Thank you very much for the introduction. And you want me write in bigger letters? Yeah, okay, I will try. I will try. It's smaller, no, definitely no. But if it's, yes, thank you, Matthias. If it's invisible or you can't hear me well, just please interrupt and say that bigger letters, whatever. So I need to mention that this talk is based on work in progress. It's a joint long-term program with Jonathan Eckhardt, who is currently in Loughborough. And also I need to apologize in advance because, as I said, this work is in progress. So I'm going to announce some results. And in fact, it might happen that I have more questions than answers. And also one more apology in advance. That seems it's like my first Blackboard talk in front of the live audience in 3 years. So I will try not to fail. Okay, the main object of my talk is here. This is a spectral problem, which looks on the one hand rather simple. X belongs to 0L, and let us put 1 here. And I need to say that decode what is who is who. So Z is spectral parameter, like dot spectral. Parameter. L is usually called its length, so it's a positive number or infinity. Omega h minus 1 log is a distribution. It's a real distribution which is locally h minus 1 on 0 L. And V is a positive measure. Positive Borel measure. Positive measure on 0 L. So this is the main object, and these are the coefficients. Also, I need to again say that probably there will be no quantum theory in my talk. Differential operators, spectral theory, yes, but quantum theory, I doubt, despite maybe there is some hidden Loughborough formulation behind. But yeah, okay. First of all, I need to say that this problem is a quadratic and spectral parameter, which makes a lot of difference and some complications. Also, another problem is that coefficients are very rough in the sense that low regularity. If you feel uncomfortable with that, you may assume for most of the talk that omega and V are sufficiently smooth, and that is basic ODE theory extends to under these assumptions for this ODE. So this is not a problem. I have no time to dive into that and explain all the details. One of the things which I want to somehow emphasize is that this spectral problem is of actually fundamental importance. Definitely, you met one a lot of times in your life. In particular, if you do separation of variables in the wave equation, you end up with this spectral problem where V is density of a mass of a string. If you do separation of variables in the one-dimensional heat equation, you end up with this problem. In particular, it appeared today in the talk of Vladimir Derkach that it's important to assume that omega is not positive. So omega might be sign change. So it's just real distribution, not no positivity, and this is crucial for us. And this is so-called in the talk of Vladimir. It was two-way diffusion equations. Also, I'm not so sure that if you consider string with damping, you have a spectral problem of this type as well. But I'm not so sure about that coefficients satisfy these assumptions. That's a little bit strange object to me, so no idea. As I said, this object, yes, you met it a lot of times in your life, but in this generality with this class of coefficients, it was introduced in our work with Jonathan almost 10 years ago. However, our work relies on the fundamental work of Mark Crane and Heinz Lange in the 1970s on the so-called indefinite moment problem, where this kind of problems appeared with coefficients where omega and v are discrete measures. What I want to say is the following one. Yes, how to understand this equation I'm not going to explain, but just I need to say that we need to look at it in a distributional sense. So both sides are distributions, and we assume that y is h1 log. That's why in particular we can multiply these things here. And what is important for me is the following thing. That's if we notation W, which is L2 log on 0L, is called normalized antiderivative. Normalized antiderivative of omega if omega, say, h is minus integral 0L W times h prime dx for all h which are h1 c0L. So in fact, if your omega is a measure, it's just a distribution function. That's it. What is important for me, and why the notion of it will appear like it will be always behind, that's derivative of y, because y is h1, is usually L2 log. And it's hard to consider Wronskians and everything, but we can introduce the so-called regularized derivatives. And regularized derivative is the quantity which is y prime plus zwy. And then this function becomes left continuous, and you can introduce fundamental system of solutions and everything. So fundamental system of solutions. That is, for left continuous functions, you can introduce boundary values and everything. And we need two solutions, usually denoted as theta zx and phi zx. It's the analog of cosine type solution and sine type solution. As I said, for this part of the talk, you can assume that coefficients are smooth and just it's just basic ODE, and replace this one with prime, and yeah. W is antiderivative always of omega. Yes, W is antiderivative of omega. That's yes. Thank you, Fritz. And then it's time to introduce the main object, another main object of spectral and inverse spectral theory. This is, I'm very slow, but nevertheless, M of z lim x goes to L minus theta zx z phi z of x. Z belongs to C minus R, and this is what? Let it be 2. If we are in the setting like all like finite interval and coefficients are regular, then here just theta and phi are well defined, and L they are entire functions, and what you get is just meromorphic function in Z. The only difference with the classical definition of Weyl-Titchmarsh function is this Z, which appears here. It's not a typo, not a mistake. We need it because it was also mentioned by Gerald yesterday and Vladimir today that if you consider L2 space associated with omega, it becomes indefinite. Moreover, our omega is a distribution, so there is no Crane space in that case. But luckily, we have left-hand side, which has a positive operator. So our proper space, in some sense, is H1 space with dots. How this is called normally? Like only when the gradient matters. Homogeneous. Thank you so much. Yes, that's why it is Z here. And for those who are familiar with spectral theory of Crane strings, this is actually a Weyl-Titchmarsh function for the dual string. And this object is called Weyl-Titchmarsh function of 1. This function has a lot of good properties. In particular, this is Herglotz-Neumann linear function. Exactly, division by z makes it Herglotz-Neumann linear. Herglotz-Neumann linear means that M of z has the following form: zv at 0 plus some constant c1, just not to, oh, b is better, 1L over z and integral r minus 0 lambda minus z minus lambda 1 plus lambda squared. Sorry for this, d rho lambda. This is integral representation of Herglotz-Neumann linear functions. It's unique, and here you might notice that there is some connection between M and spectral problem 1. In particular, linear term is exactly the point mass of V at 0. There is tempting to write instead of B point mass for V at 0, but this is not true. L, you can recover lengths out of M, just a pole at 0, like residue of M at 0. And rho is a positive measure. That is rho positive measure on R, and it satisfies Poisson's summability condition in order to this thing to make sense. Also, we remove 0, that is, pole is always isolated out of rho. That's d rho 1 over lambda square is finite. The good thing is you can associate properties of rho with the singularities of M. It's well known that is singularities of M. This is the topological support of rho. And we also can say that this is the spectrum of 1. In fact, there is a spectral theory behind 1, that is, it's possible to associate, introduce strange Hilbert space, introduce a linear relation, like not an operator, it must be a linear relation. And then this rho is a spectral function, in the sense that the operator part of the corresponding linear relation is unitarily equivalent to multiplication operator in L2 with the weight function rho. What else I want to say? Now it's time to state the main result. I believe now must be visible very well. So this is theorem. I will call it A, just to keep. So all the results are joined with Jonathan. That's why I'm not going to state explicitly every time that. But I said that I'm going to announce only one theorem and try to explain what's behind it. A Herglotz-Neumann linear function M is a Weyl-Titchmarsh function of 1 with L equal to infinity and coefficients omega and V satisfying 0 infinity. Here is Wx minus x square x dx plus integral. Not very important, but nevertheless. Finally, let us put 3 here, if and only if the following 4 conditions are satisfied. First of all, M is analytic. Oh, it means analytic because it defines away of R, but clearly it admits analytic continuation away of the support of rho. So M is analytic at z equal to 0, and moreover, M at 0 is equal to 1. Second of all, M admits M is meromorphic on C minus 1 over 4 infinity. Condition number 3, that's the discrete spectrum of the corresponding problem. The spectrum which lies from minus infinity to 1 satisfies the following condition. That is some lambda, which is in sigma rho smaller than 1, minus 3 over 2 plus lambda in sigma 0, 1 over 4, 1 over 4 minus lambda 3 over 2 is finite. And the last one, integral from 1/4 to infinity, lambda minus 1/4 lambda cube, and log m lambda plus E0, the lambda is greater than minus infinity. So what is here is that's a complete characterization of Hergotz-Nevan linear functions of the problem 1, such that its length is infinity and coefficients satisfy these somehow strange-looking conditions. On the one hand, like before commenting on all these conditions and explaining why exactly this class of coefficients, that is why this strange choice, let me say that this theorem is, in a certain sense, the analog of this pioneering work of Rowan Killip and Barry Simon on the characterization of a solution of spectral problem, inverse spectral problem for Jacobi matrices with L2 coefficients of some L2 perturbations, and Schrödinger, one-dimensional Schrödinger operators with L2 potentials. In fact, this result is in spirit is much closer to their work on Jacobi matrices rather than to Schrödinger, and I will explain this why in a moment. In fact, everything can be restated in terms of spectral measures, because there is only one issue, because spectral measure is not uniquely determined out of M, because there is this linear term. It is 18-point masses at 0 does not allow you to recover rho uniquely. But we can restate it as in the following way. That is corollary. A rho is a spectral measure of one with L equal to infinity and coefficient satisfying 3, if and only if, first of all, 0 does not belong to the support of rho. Second of all, it's with I, then it's 2I. Where is it? Sup rho is discrete in minus infinity 1/4. Condition 3, let me call it 4 and 5. 4 easily translates into, 4 holds true. And 5 translates into the this one. It's 1/4 infinity lambda minus 1 lambda cube. And here it's log d rho lambda d lambda greater than. That is, condition 4 is just the condition on the absolutely continuous part of the spectral measure rho. So in fact, this result says that for this class of perturbation, so you consider this as a perturbation theory result where omega 0 is just this weight, more or less, and V is 0. And it says that if you stay in this class, then you can get absolutely arbitrary singular spectrum on the interval 1/4 infinity. Also, this result says that the absolutely continuous spectrum is also supported on 1/4 infinity. Yes, time is much faster than I expected. But let me say the following thing. So maybe let me try now, to comment about the meaning of all these conditions 1, 2, 3, 4. For those who are familiar with the work of Killip and Simon, then condition 1 is nothing but local solubility condition. Condition 2 is Weyl type condition. Condition 3 is Loughborough type condition, and condition 4 is quasi-Sergio. The meaning of that I will try to explain in the next couple of minutes. So first of all, remarks. Condition E, actually, there is, as I said, the object one is of fundamental importance because, as you see, 2 establishes a map. So you can consider definition 2 as a map from 2 says that we have L omega V to M. So the collection of all such triple we prefer to call generalized indefinite string. So it's a strange name, but who cares? And we have the class of coefficients, and we have a map into the set of Herglosny-Wallina functions. The result theorem, let me say one, that this map is not only bijective, that is, it maps it says that for every Herglosny-Wallina function, there is a unique triple L omega V such that M is Herglosny-Wallina function. But also this map is homeomorphic. This is our result from 2016. Actually, despite that this object looks a little bit strange, behind it there is 2 times 2 canonical systems, like the theory of actually Crane and the branch. And this theorem is nothing but a complete solution of the inverse spectral problem for this class of strange-looking problems here. And its fundamental importance stems from the fact that actually it says that generalized indefinite strings, they serve as canonical model of self-adjoint operator with simple spectrum. So it stays on the same level as Jacobi matrices, Krein strings, and 2 times 2 canonical systems, as I said. So in fact, condition E here, first of all, by theorem 1, it says that already if M is Herglosny-Wallina, there is a string. So condition I guarantees the existence of a string. Moreover, analyticity says that there is no pole. So L must be infinity. So condition I says that already we have such an object. Yes. No. Here L is arbitrary. Yes. Here L is arbitrary. But in my theorem, M is analytic at Z equal to 0. And analyticity means that there is no pole. That's why L must be infinity. So it's already gives you that. But also analyticity at 0 is already very strong requirement, which says that the operator which stays behind 1 has bounded inverse. And in fact, this can be characterized completely in a sense that, and this is this result is rather fresh, and it's going to appear in the volume dedicated to the memory of Sergei Nabokov, who passed away, I think it's 2 years ago. And the result is theorem 2. That's M is analytic at Z equal to 0, if and only if, first of all, as I said, L must be infinity because no pole. And the second condition, that's lim sup x goes to infinity x integral x from infinity to ws minus c squared ds plus integral from x to infinity dv is finite. This is, it will be 6. So clearly this condition is much weaker than condition 3. So that's why it guarantees analyticity. In fact, the quantity which appears here, it allows you to estimate the bottom of the spectrum of problem 1 from above and from below. So it's a qualitative estimate which actually goes back to the work of Katz and Crane in the 50s. The constant C here, which is this condition must be satisfied for some C. And clearly this C is nothing but if it's satisfied, then C is given by, where to put it? Just, okay, and then C is lim 1 over x, 0 x, ws, ds, x goes to infinity. And in fact, one can even show that M at 0 is equal to C in this case. That's and result on low energy asymptotics. It actually goes back to our work with Gerald Teschl. It was 2016 or 17, something like that. So yeah, this is local solubility. That M is meromorphic. It's a perturbation theory result. So behind it is Weyl theorem on stability of the essential spectrum. Because of analyticity, it's really not a trivial task to associate operator with one. But once we have analyticity, we know that operator has bounded inverse. This means that we can actually apply the inverse of the negative second derivative to that guy. And we can consider as a quadratic pencil with bounded linear operators. So if I go to remark B, then if we set S0 as infinity omega 0 with W0 to be 1 over 1 plus X. Oh, yeah, just omega 0 squared. And we, the corresponding M function can be computed explicitly, so it's a completely solvable model. This is minus I minus plus 1 over 2. And then we can develop some sort of perturbation theory. So as I said, since we are analytic, we can analyticity at 0 implies that we can associate S of Z, which is 1 minus Z K omega minus Z square KV with 1, where K omega is, let me define it as like this, Fg H1 H dot 1 0 chi F G star. Fg belongs to H dot 1 0 0 L. So we can define associated operator just in the usual way with bilinear form. And if we have condition 3, this guarantees that both operators defined in this way, K omega and Kv, are bounded. This simplifies the dealing with this guy here. In particular, we can introduce the operator T. I think I do not need even tilde, which is like the way we, standard way we try to linearize the corresponding pencil, Kv 0. Because V is positive measure, Kv is a positive operator, we can define self-adjoint square root of that. And it turns out that, because again, due to analyticity, that sigma of T minus 1 is equal to sigma. That is indeed, we can relate the spectrum of 1 to the spectrum of this operator matrix. I need to skip a lot of details, unfortunately, but now we are in the setting that we have a 0. That is, we can do perturbation theory. And it turns out that if we take T minus T0, 0 means that this everything with 0 subscript. And we take square and consider Hilbert-Schmidt norm of this guy in the corresponding H1 times H1. And then the Hilbert-Schmidt norm is nothing but 2 times the left-hand side in 3. So this quantity here on the left-hand side is nothing but the Hilbert-Schmidt norm of the difference T minus T0 in the corresponding Hilbert space. So if from this perspective, we characterize relative Hilbert-Schmidt class perturbations of this particular string here. In particular, we, in view of condition 4, we say that absolutely continuous spectrum is preserved under Hilbert-Schmidt class perturbations. But also it says that we can have arbitrary singular continuous spectrum. Okay, I have 3 more pages to present, and I just at the end of number 3. Oh, so probably how much time do I have? -2. Yes. Let me maybe try then to make a disaster. As I said, I did not give Blackboard talks for a very long time, and I was very slow. But just a couple of quick remarks, because there is also Camassa-Holm equation, which is not on the Blackboard yet. Two remarks. First of all, if you want like to prove something which is like Kilip-Simon type results, like characterization for the special class, this requires some sort of a very serious development of direct and inverse spectral theory for your concrete class of operators. And actually we were successful, like we accomplished that during the last 10 years, I believe, and this is the confirmation that we did well. Behind all these things is, of course, trace formulas. Or leap tearing, these kind of things, and trace formulas, they, of course, go back to the classical trace formulas by Buslaev and Fadeev, where you have transmission coefficients and you go to boundary values. Of course, in Buslaev and Fadeev, transmission coefficient is H infinity function, and you have everything good. Here, life is much more complicated. In particular, that was one of our main struggles. That is, we were forced to prove representation, like in terms of boundary values, result for a new class of meromorphic functions. But definitely no time to go into that. For me, it's a bit surprising, or mysterious, I must say, that all these leap tearing type estimates for Jacobi, one-dimensional Schrödinger, and here there is always exponent 3/2. I have no idea why, and I'm curious why it's always like 3/2. Yes, Camassa-Holm equation, this in the title, is some sort of spoiler. So we were not just, our motivation was not like just, we can do this, that's why we proved it. Actually, behind it is Camassa-Holm equation, for which problem 1 is isospectral problem. Actually, it's the isospectral problem for the Camassa-Holm equation looks very much similar. Actually, for the so-called conservative Camassa-Holm flow, there is 1/4. And you consider things on the line. What you need to do in order to connect this spectral problem with 1, you just need to use simple change of variables. Send x to e to the power x. And for the Camassa-Holm equation, H1, the normal H1, is in some sense phase space. So the Hamiltonian for the Camassa-Holm equation is exactly the square of the H1 norm of your solution. And from this perspective, this result, if you do on the half line this change of variables, you would be able to transform 3 into the condition that, because for the Camassa-Holm equation, omega is u minus second derivative of u. And if you do this change of variables, this means that 3 goes to u minus 1 belongs to H1. So this is also interesting for, because our motivation was like how to understand the Camassa-Holm equation by using the inverse scattering transform approach. On the one hand, it confirms what we know for Toda and KdV. That's for KdV is well posed with even H minus 1 initial data. So Bourgain was for L2, and for H minus 1 is recent result by Kilip and Vishan. The problem is that we are not allowed to use the classical inverse scattering transform approach because we have a lot of singular continuous spectrum for this data. So it's a very intriguing and difficult problem in this business, like how to understand KdV, Toda, Camassa-Holm with low regularity initial data. But what I want to say is that Camassa-Holm equation, my very last comment, sorry, I'm disaster. It's much more interesting model in some sense than KdV, because for the Camassa-Holm, dynamics depends on the choice of initial data. So it includes KdV dynamics, in particular if you do things like that, it's more or less very much similar to KdV dynamics. If you do omega and v discrete measures, you are in the mode of multiplicans. This is Toda. If you do v, which behaves like dx, this is NLS. But this result, because you can transform the whole line into half line, we can define the Camassa-Holm flow on this class of initial data. So somehow we will have step-like data which has decay at very fast decay at minus infinity, but u minus 1 in h1. And this allows us to apply the inverse scattering transform approach in this setting. I'm really sorry that I need to finish at this point. 5 minutes, disaster. Sorry. My apologies for that. It's I didn't expect. Thank you so much for being so patient.